Okay. So we'll continue the fascinating subject of out-of-order execution today. Hopefully you've gone through some of the animations that I suggested that you go through. That's the best way of understanding it. Okay. Yeah, and hopefully we'll cover a little bit more data flow. Now you will see that an out-of-order machine actually builds a data flow graph internally without the programmer being aware of it. And then we'll jump into other topics like superscalar execution that are there, which is an orthogonal concept to improve performance even more. Okay, so these are the readings. Please do them. We'll talk about that reading a little bit more. And combining branch prediction. Next week, we're going to cover branch prediction, which is another fascinating topic. Okay, so we're going to continue this. Recall that we were doing this exercise where we were really simulating the execution of this program in an out-of-order execution processor with imprecise exceptions to begin with. And we have these 4 stages, and add takes 4 cycles and multiply takes 6 cycles. I'm not going to go through the simulations that we did yesterday, but basically out-of-order execution enables the out-of-order dispatch of these 2 instructions that are independent, as you can see over here. And as a result, it gives you better performance, like 20 cycles as opposed to 25 cycles in this case. Okay, and if you remember, we were doing the simulation. I'll just to jog your memory, I'll just talk about this again. Remember, this is the register alias table that we use for renaming. Renaming is important. Whenever an instruction gets renamed, you basically associate a tag with the destination register such that the dependent instructions know which value they should wait for. Basically, for example, this instruction multiply, if you recall, we renamed it in cycle 2. And renaming means that you first, you read the source registers, put them into the reservation station entry that you allocate for this. And then the destination register gets renamed to the ID of the reservation station entry. So at this point, R3 is a name, and it doesn't really exist. It's not really important for anything else in the system, except the next instruction that's going to source R3 will know that it's going to come from X. So R3 is renamed to X. And whenever this instruction multiply produces X, it's going to broadcast the tag X. And everybody who's waiting for X will capture the value that's also broadcast. So that's the idea. Renaming enables linking of instructions through these tags. So if you think about it, this R3 is a mechanism for communicating the result of this instruction to the source as an operand of this instruction. And we're basically renaming to X. Okay? So every instruction, when it's decoded, it renames its destination register, assuming it's writing to a destination register. And before that, as you know, it reads its sources from the register alias table and places them into the reservation station. Okay, so I already said this basically. R3, the new value of R3 is produced by the reservation station that is identified by tag X. Okay. So actually, I will have a question later on related to this, but we didn't really need to rename it to X, right? X happens to be the reservation station ID over here, but you could have some other namespace. You could have some other ID associated with it, as long as you can ensure that this instruction that's producing this value of R3 is connected to the instructions that are consuming the value. You can give it any name. It doesn't have to be the reservation station ID. It could be the reorder buffer entry ID. It just needs to be a unique identifier that enables the communication of this particular instance of R3 after it's produced to all of the dependent instructions that need that particular instance of R3. Okay? Okay, so this is cycle 3. Again, I'm not going to go through this animation again. You should do it on your own. We did it last time. Basically, this instruction becomes available in cycle 3, so it can execute, and it starts executing, and the next instruction gets renamed in cycle 3. And as you can see that the next instruction is sourcing R3. When it reads its sources, R3 and R4, it realizes that it's going to wait for tag X to be broadcast. And when it's tag X going to be broadcast, it will be broadcast when this instruction finishes execution. And then it will broadcast tag X, and this instruction will capture that tag X and capture the value that's also broadcast. So that's how you link instructions. So it's very simple conceptually, actually. The implementation is actually horrible, as we will talk about. Okay, horrible in terms of area cost, complexity, and hardware cost. Okay, this is cycle 4. This instruction is executing. And now the third instruction gets renamed. Now you know the drill very well. You read the sources, put them into the reservation station, and you rename the destination to, in this case, the reservation station ID. And you can see by just looking at this picture that both sources are valid, which means that this instruction can execute in the next cycle. In the next cycle, it starts executing, and then the instruction after that gets renamed. And this is an add, so it allocates a reservation station entry over here. Okay, it already did it quickly, sorry. Yeah, basically, this is, yeah. You see that this, it's also available, it will execute in the next cycle. So we've enabled out-of-order execution because we're able to buffer the instructions that are not available, but the instructions that are available are also buffered and they can execute. Whereas this instruction is going to wait for some time. These instructions that are out of the program order that come after this instruction over here can now execute. That's the beauty of the reservation station. Okay, I'm not going to go through this. We've already renamed all of this. Okay, so now this is cycle 7 is the cycle where all instructions are renamed and decoded. And some instructions are executing in the machine. Clearly, we're not tracking everything over here. And we discussed what happened to R5. R5 was renamed to A initially. Now it's renamed to D because this instruction is writing to R5. It's renamed R5 to A. And all of the instructions after that are going to reference R5 as A. And this instruction actually references A. But this instruction renames R5 to D. So all instructions after this will get the tag D, such that they can get the correct value of R5 from the result of this instruction. Okay? So you're basically linking producers to the consumers. Producers are producing a tag associated with their register. Consumers are using that tag until that tag for that particular register gets replaced with some other tag. Okay. So cycle 8 was the interesting cycle. This is where we ended. This was really the interesting cycle where this instruction finished execution, as you can see over here, and also some other instruction finished execution. Let's take a look at this instruction. So when this instruction finishes execution, after 6 cycles, as you can see, it broadcasts its tag, X. As you can see, this will hopefully animate. And you can see that X is being broadcast to all locations in the machine where you see tag. So all of the places where you see tag, you should send the tag, because there might be some instructions waiting for that tag. And the instructions that are waiting for that tag and that do not have it valid over here capture the value. So value gets also broadcast, and these capture the value such that they become valid, and the value becomes stored over here. So there are two things that are waiting for value tag X over here, R3 in the register file, and also the first source of this instruction in reservation station A for the add reservation station. And they both capture the value because the value is not valid yet. And they store 2. That makes sense, right? The first instruction multiplied 1 by 2, it produced the value 2 in R3, and R3 captured it. And the instruction that's waiting for that value also captured that. Now this instruction can execute because both of the sources became valid. Okay? So now you should ask yourself, what is it required to enable this? Right? It's actually a lot of circuitry, as you can see, right? We're storing all these tags, okay? But whenever we're doing a broadcast, we're sending the tag of the instruction that's just finished execution everywhere in the machine where you see tag. And all of those locations have comparators comparing the tag that's stored to the tag that's broadcast and they're checking equivalence. If those are equal, then you know that the tag being broadcast is the thing that you're waiting for. And of course, the instruction should also, the tag you're waiting for, the value you're waiting for should not be valid as well, because you may have a stale tag over here. So basically, it's a lot of comparators. You have a lot of comparators here, you have a lot of comparators here, 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 here. So if you want to have lots of instructions, lots of reservation stations, the cost of this increases. And also, you need to broadcast the value, so you need to have buses when you broadcast the value. If the tag matches, and if this is not valid, you capture the value and write the result in the appropriate location, just like we did over here. So that's also cost. Now, there's also another cost, which is cycle 8. There's something else that's happening. The adder happens to finish the instructions executing also, so it broadcasts the tag of that instruction B, and you need to do the same thing. Basically, B also needs to be broadcast in the same cycle at the same time to all of the locations that are marked as tag over there. So you need to have not just one comparator. We had a comparator for the multipliers broadcast tag. You have another comparator for each location to capture the tag that's broadcast by the adder. So now you have 2 comparators per entry, right? That doesn't sound very good. Yes?
So in this example, we don't have a reorder buffer.
Yeah, exactly. This is imprecise exceptions. In this example, we don't have a reorder buffer. I'm going to introduce that later on. Yeah.
Okay, you said that it could happen if we have stale data.
Yeah.
When the valid bit is 1, but it still has the tag from the previous.
That's right, yes.
When could that happen? Because the valid bit is 1.
That could happen when you flush the pipeline for some reason.
Okay.
Yeah, don't worry about that now. It's not, yeah, when you actually don't, if you never flush the pipeline, it shouldn't happen. But if you flush the pipeline for some reason, and if you don't reset the tags, then it could happen. Okay, so now you see how this works. I mean, your colleagues have very good points. We don't have a reorder buffer here, right? We are barely broadcasting, we're really updating the register file here, register alias table. So reorder buffer will change this a little bit, but not by much. Basically, we're not going to update the register file. Okay, I'm not going to go into that right now, but let's finish this example. Okay, you also broadcast as result. So that the ones that are waiting for the result, which were waiting for tag B, capture the value. And now some of them can start executing. Well, this one cannot start executing still because it's also waiting for C to be broadcast, as you can see, right? Okay, so this is the third slide. This is the third thing happens in cycle 8. Basically, these other instructions keep waiting because their values are not available. Their sources are not available. Okay, cycle 9, what happens is, assuming you had some reorder buffer, you would actually write this result, but ignore that for now. Basically, here I really ignore timing as much, right? We'll talk about timing very briefly, but we're not really going to do justice to the timing. I'm assuming that you're broadcasting the value, capturing it, and writing it in one cycle, right? That's a lot of assumption. Yes, there's a question in the back.
Does every instruction in the ALU have its own reservation station?
So every instruction, so this is a reservation station for the adder. And yeah, for every instruction that you've decoded and renamed, you need to have a reservation station entry. Absolutely. So in this case, we have 4 reservation station entries. In this case, we have 4 multiply reservation station entries. If you need more, you stall. Okay. So in this cycle, a similar thing happens. This add R8, R9, this add finishes over here. So it broadcasts its tag in cycle 9. And you can simulate it. You can see that, I mean, we didn't animate it fully. But what happens is this instruction, this add, let me see. Yeah, it was adding R8 and R9. It was this instruction over here. It basically broadcasts tag C, and tag C gets broadcast everywhere, and everybody who's waiting for tag C captures the value. So this value should change to 17, and this value should also change to 17 because 8 plus 9 is 17, right? Okay, so that happens. And now in the next cycle, this instruction can start executing, right? Okay. And then cycle 10, cycle 11, I'm not going to go through this animation, but you can convince yourself that the same thing happens. Whenever an instruction finishes, it broadcasts its tag and the value. So in this case, this is instruction, the first add, which was this add. It broadcasts A. So if we go back, who's waiting for A? Looks like nobody in the register file is waiting for A because R5 got overwritten, if you remember, by this instruction. But there's someone who's here in the reservation stations waiting for A, and that's instruction identified by tag D. So that captures value 6. Now it still cannot execute because it's still waiting for the other source. So somebody's going to produce that source. And we will see who produces that source. And it will be this instruction over here, multiply. It produces the source by multiplying R7 and R10. And it's in, wait a second, that multiplies here, Y. It broadcasts Y, and Y gets captured by R11, which is destination. And it also gets captured by this reservation station entry. So you get 136 over here. And that's cycle 15. Now this instruction can start executing. And it's the last instruction to execute and finish. And that's how you get to cycle 19, when it broadcasts an update. Basically, it broadcasts the value, broadcast tag D. And there's only one thing that's waiting for tag D, which is the register 5 over here in the register file. Because we didn't decode any more instructions, there's nothing else that's waiting for that value. So it updates the register file with the value, and we're done with this program in cycle 20. Yes?
Cycle 9, we assume that the memory has multiple write ports.
In which cycle? 9. Let me see. 19.
9, you don't have to step back. If you look at the cycle of 9.
Oh, okay, I see what you mean. Yes, so that's a good point. Basically, we're assuming that there are multiple write ports in the register file. So that's an assumption. If there is not enough write ports, then you basically need to serialize. There needs to be another mechanism that says, okay, you wait and broadcast in the next cycle.
Those instructions are independent.
Exactly, yes, exactly. So these are real issues that real machines face, actually. If you don't have enough write ports, you delay the execution write back a little bit. Okay, so very good questions. So I'm going to skip since we're done. But hopefully you understood the example. If not, you should go and, yes, another question.
If one of those reservation stations of a functional unit is full, does it stall with dispatching?
Yes, exactly. So basically, if you cannot dispatch, if there's no available reservation stage, that's step 1, if you remember.
Does it stall the dispatching for just those instructions or for all instructions?
So it stalls dispatching because you need to dispatch in order, not dispatch, you need to allocate a reservation station entry in order. Because everything else is dependent on it in terms of renaming.
But instructions for other instruction units can be dispatched.
So I think we need to clarify the word dispatch. So let's assume that you have another add in the program and this is all full, right? You don't have space here. You need to stall the machine, right? Yes, exactly.
If there's a multiplier, then it can be
No, because you're renaming in order. If there's another, so if that add was not there, if it was a multiply, yes. But you cannot take an instruction that's after the add and rename it, because that will break all of the linking that we do in terms of renaming, right? So renaming is all in order, in sequential order, so that you can link the instructions. You cannot do out-of-order renaming. I mean, you could, but it complicates the system a lot, actually, and people don't do it. Okay, so I think I already answered this question, actually. What is needed in hardware to perform tag broadcast and value capture? Basically, lots of comparators. Whenever you broadcast a tag, you compare it to every possible place any tag is stored, so you need comparators. And you also need to broadcast the value. So you need to make the value valid with that comparison result. and you need to wake up an instruction also. After you broadcast the tag, there is some machinery also that I didn't really show that checks whether both sources of the instruction are actually ready. If both sources are ready, then in the next cycle, the instruction can start executing. But of course, multiple instructions may become ready at the same time, so you need to handle that case. If multiple instructions in the same functional unit become ready, you need to say, okay, you go first, and the next one goes first. So there needs to be machinery for that also. Okay, I already answered this question also. Does the tag have to be the ID of the reservation station entry? No, not really. We just use that for convenience over here. The tag can be any unique identifier that ensures that that particular instance of a register is named uniquely, so that anyone that needs that particular instance gets that unique name. So you could come up with your alphabet for renaming. Okay, what can potentially become the critical path? I think I already kind of said that also. This is actually one of the most difficult parts to design in an out-of-order engine. You broadcast a tag. Some instructions that are waiting for it need to capture the value based on the equivalence of the tag, and based on that, you need to determine the instruction wakes up. So this is called a loop, actually. This is called the scheduling loop in an out-of-order engine. You're really trying to figure out which instructions should become ready based on what previous instruction produced the value. So this could actually very easily become a critical path. And in the previous slides, I didn't really talk about timing, and we're not really going to a lot into timing, but timing of this is not very easy to handle, and people do a lot of tricks today. And how can you reduce the potential critical paths? That's something for you to think about, perhaps. Okay, now let's do this exercise. So this was our example, right? If I gave you this code, you would be able to convert this to a DataFlow graph, right? You remember the DataFlow graph has nodes and arcs. Nodes are the operations. Arcs are the values that are needed by the operations. So it's easy to take this and do a forward engineering and basically have an arc for multiply, have a node for multiply, have a node for add, and connect the output of the multiply into the input of the add, right? So we can do that. That's simple. But if you look at the state of the machine in cycle 7, you could do the reverse engineering of this. What you could do is by just looking at this thing, you can really get the DataFlow graph. Shall we do it quickly? I'd like to do at least for part of it, but I don't know where my thing is. That's not. Okay, let's do some white paper over here. Well, I want to be able to see this also. What happened? It has a mind of its own. Okay, maybe I don't have what I really need. Oh, okay, this is it. Cool. But I don't have the fancy picture, I guess. So you're going to have to do without the fancy picture. So, oh, there's some intelligence here. Or maybe you're the intelligence, yes. So it's not machine intelligence in the end, it's human intelligence, as you can see. Okay, so basically, if you have this thing, we can construct the DataFlow graph easily. I'm not sure if it's going to be that easy over here. But I think this is enough. Actually, we don't really need, well, we may need the register file also. Basically, by just looking at this thing, I know what's going on, right? For example, this is an add instruction. Why is that 0? Okay, it's 0, fine. One of the inputs is 4, and the other input is really coming from x, right? And, okay, now let me look at x, just for fun. This is a multiply instruction. One of the inputs is 1, and the other input is 2, and it produces x. Sounds good. I'm going to connect them, right? Now we're forming the DataFlow graph of this thing. Okay, let me switch to this one. That looks interesting. This is an add instruction, another add instruction. I don't know where to put it. I'll put it over here. Both inputs are ready. Which, one is 2, one is 6, right? Good. And then let's take a look at this one. This is another add instruction. Both inputs are ready. One is 8, one is 9. And okay, I should have done something else also. This is X. So this ad is going to produce A. This ad is going to produce B. This ad is going to produce C. Okay, now I have something interesting over here. This is a multiply instruction. And it seems like it's getting as input B and C. And it's producing Y. Sounds good. So what is left? What is left is this instruction that's an add instruction that's getting input A and then Y and then producing D. That's our data flow graph. And we can now attribute, we can reverse engineer these tags to be registers and values also to be registers. Let's take a look at how we do that. And we look at the register file for that. So D is R5. So this better be R5, I assume, because there's no other definition of D anywhere. B is R7. Where's B? So this is R7. C is R10. So this is R10. I don't know if you can see that, but this is R10. And what is this? Y? Y is R11. So that's R11. X is R3. So that's R3. A, I have no idea, because A is not here. But you can probably reverse engineer it, right? So I'll let you figure the rest out. Let me actually see if I have it here so that I don't need to switch. Say it again?
I think it's R5 because A was overwritten by D.
Exactly. So that's how you figure that out. So basically, the way you figure it out is D is here, right? But how do you know that it was overwritten by D?
The previous slide.
You mean over here?
Yeah, it was in the previous slide.
What do you mean in the previous slide? Here?
No, when you had it on the projector. I have to print it out here.
Oh, I see, I see. Yeah, but that's cheating, right? So basically the question is, it's clearly somebody overwrote the A, right? But which one? I'll let you think about that. Yes?
It can't be X because X is the input
Exactly.
for A.
Okay. It can't be X, that's good. Exactly, so you can eliminate basically, you can do the process of elimination. Absolutely. Good. I'll let you think about this. But basically you can reconstruct the data flow graph like this. We won't, I mean, I didn't do the values over here, but in the end what you get is a data flow graph that looks like this. Right? And then, of course, you don't have it initially. You start with this figure over here, and then essentially I reconstructed most of it, but didn't complete. For example, 8, 9, you can, based on looking at the values, you can say that, okay, this is R8, this is R9, because there's no other, you need to ensure that there's no other way to produce that value somehow, but it's also clear because it's not connected somewhere else. So based on some assumptions, you can really fully reconstruct this. So this is, for example, yeah. Okay. Does that sound good? Do you believe that you can reconstruct the graph completely? Yes.
Can we also say that it can't be Y because Y and A, they are two inputs for the same addition.
Y and A.
Is it safe to say that?
No, you cannot say that, right? Because this instruction may actually rename the same register, which is R11. And you don't know that at this point. And I don't remember if you could actually fully reconstruct this, but I'll leave that for you as an exercise, because this is the fun part. Okay. Does that sound good? So basically, what we've done is just by looking at the state of the machine in cycle 7, reconstructed, well, at least most of the data flow graph. But we didn't reconstruct the entire program because we don't know some of the orderings, right? So we don't know this. This is the program that we started out with. But we don't know if, by just looking at the data flow graph, we don't know how to order some of these instructions. We know that this comes before this one, because there's a flow dependence, but we don't know whether this should be ordered before this or before this. These are happening all in parallel. Actually, I'm going to switch to this data flow graph. Basically, you cannot really fully reconstruct the sequential order, because the machine is really housing the data flow order. So this is really a data flow machine internally, as you can see, because we constructed most of the data flow graph. It doesn't matter if we reconstructed R2 or R1. You cannot reconstruct it maybe by just looking at it, because this is internally a data flow machine. It doesn't care if it's R2 or 1. What it really cares about is the name that we've assigned over here. Does that make sense? So we've successfully translated the sequential program into a data flow graph internally, and just by looking at the state of the machine, we cannot maybe fully reconstruct the sequential program because it's not sequential anymore internally. The way it's going to become sequential is we are going to reorder these instructions later on. Yes?
But you can reconstruct it that it is semantically equivalent.
Yeah, absolutely. It's exactly, that's why it works. It's semantically equivalent, but it's not, you cannot reconstruct the sequential order because you're really executing things in data flow order. That's why this is a data flow machine internally. Okay, so now let's go back to this thing. And I'm faster than the human intelligence, I think. But I'm not as good, perhaps, because it's not working. Okay, why didn't this work? Okay, thank you very much. Because I picked the wrong one. Okay, so, okay, I'll let you, please do this exercise on your own. It's a very easy exercise, and we have homework questions related to this also. Okay, there are a bunch of other questions over here, which I'm not going to really fully answer, because there are a lot of design choices that you make in an out-of-order machine. And that's actually what makes this design extremely exciting, right? When do you deallocate a reservation station, for example? That's a question. Do you deallocate it right after execution? That's probably a good idea, because you don't really need to hold on to reservation stations after you're done with them, right? But different machines make different choices, actually. Should the reservation stations be dedicated to each functional unit, like what we've shown in the picture? Adder has a different set of reservation stations compared to the multiplier. Or should they be global across functional units, as opposed to having 4 reservation stations for the adder or 4 reservation stations for the multiplier? Should you have 8 reservation stations that are shared? So what are the benefits and downsides? Basically, this is the trade-off between centralized reservation stations versus distributed reservation stations. Now, one trade-off is if it's centralized, it's going to be a bigger data structure, assuming you keep the same number of instructions. And now it's going to be bigger memory, so it may not be as easy to design. But if it's centralized, you may actually get better balance. For example, if in the case that you mentioned earlier, if you have a lot of ads, you're not limited by just 4 ads over here. Because it's centralized, you can accommodate more ads. Whereas if you had 4 reservation stations for 4 ads and 4 multiplies, if you just get 4 ads, the machine stalls after. If you get 5 ads, the machine stalls, right? You have a problem. But if you had 8 reservation station entries that you can use globally for all functional units, you could accommodate instruction mixes better. You can have 5 ads plus 3 multiplies, for example. So these are classic trade-offs between centralized and distributed. If you have distributed, you can actually specialize the reservation station for the functional unit also. I didn't show you branch functional unit, for example, but branch doesn't, like multiply and add are similar in the sense that they're binary operations, but you may actually have unary operations or operations that don't need 2 source registers, right? So in that case, you can actually specialize the reservation stations. If you have only 1 source register needed, your reservation station doesn't need to handle 2 tags, right? It can handle it needs only 1 tag and 1 value. So you can basically specialize the reservation station to functional units if you're more distributed. As you get more centralized, the reservation station needs to be more general purpose, and also it needs to be bigger. As a result, it becomes difficult to design. So usually, current machines make the trade-off such that the reservation stations are usually distributed, but they may not be serving only 1 adder. For example, you have an adder reservation station, and you may have multiple adders over there, 4 adders, for example, as opposed to having only 1 adder. Okay, another question. Should the reservation stations store data values, or should there be a centralized location where all data values are stored? So this is actually another form of inefficiency. If we go back here, there are lots of values stored here. And these are, if you're in a 32-bit architecture, it's 32 bits. If you're 64 bits, it's 64 bits. So you have lots of values in the register file. You have lots of values here, lots of values here, lots of values here, lots of values here. And if you keep increasing the size of this, you need to add more values. So people quickly find out that these values are actually a lot of storage. And if you actually broadcast them everywhere in the machine, that's a lot of power and energy also. So maybe it's good to ask the question, should they really be stored here? Or should we have somewhere else to store them? And while keeping the same principles of operation. And the answer is, yes, we should have somewhere else, basically. So in the worst case, for example, if you're always writing to a particular register, you're really storing the value of that register over and over and over and over and over, right? R3, for example. Or if you're always reading if you're always reading from the same register, if you're always reading, for example, R1, if all your instructions, for whatever reason, are reading from R1, all of the sources are R1 over here, the value is the same over here, the value is again the same over here, same over here, same over here. So you have a lot of duplicate values in here. So people have found out that you could actually reduce the storage that you have by not storing the values over there, but storing them in a physical register file that's separate, and essentially using the ID of the register, of that physical register, as the tag of the instruction. Basically now, whenever you're renaming a register, you don't rename it to the reservation station entry, but you rename it to the physical register entry. So I'll quickly get to that later on, and there are trade-offs associated with it. Okay, timing, I'm going to skip this, but think about exactly when does an instruction broadcast its tag. You need to time this well so that you actually don't increase your critical path clock cycle time. I'll get back to this physical register file with example from real engines. So there are many, many other design choices for out-of-order execution engines that I'm not going to cover, and other things like exceptions actually complicate this a bit also. So let me become a little bit more realistic, and then I'll introduce some of the concepts this way. So basically, this is an exercise with precise exceptions. How do you do this out-of-order execution with precise exceptions? The fundamentals are essentially the same. Before, in this example, as some of you noticed, we're updating the register file right away. Don't do that, basically. Use a reorder buffer to reorder the instructions before committing them to the architectural state. So the way this works is an instruction updates the register alias table when it completes execution. And this is called, so we're going to actually have two register files now. This is called the front-end register file. And now we're going to introduce a separate architectural register file, and an instruction updates the separate architectural register file when it retires. So this front-end register file is very similar to what we've shown. But the separate architectural register file will be updated when the instruction is the oldest in the machine and has complete execution. Makes sense, right? That's really your architectural state now. So basically, the architectural register file is always updated in program order now. Okay, so let me actually show this very quickly again. Okay, I'll use this one, and thank you. So basically, thank you even more. Okay, I'm going to use this one. I mean, it doesn't matter which one. Oh, okay, that's a better one. So basically, before we had this a register file. Now this is our, I'm going to call this the front-end register file. It's at the front end of the machine. It's used for renaming. And whenever instruction finishes execution, we're going to do exactly the same thing. But we're going to add two other structures over here, reorder buffer and an architectural register file. This architectural register file will hold the architectural state. So this register file will be used for renaming. This architectural register file will be used for precise exceptions. And when an instruction finishes, it writes its value over here and also to the reorder buffer. And when instruction becomes the oldest in the machine, you take the value and update the architectural register file. So architectural register file is again R1 through R11 over here, but you update it when the instruction actually finishes in sequential order. Now the correct programmer visible state is over here. This is completely microarchitectural. It's not visible to the programmer. So you don't have imprecise exceptions anymore because this is what really matters. It's always updated in program order. Right? So that's the solution. This is very, very similar to what we've seen with the reorder buffer And reorder buffer enables us to update this register file in program order. Okay, simple, right? But we're complicating the machine, as you can see. So on an exception, what happens? Oh, okay, you guys can see it, that's good. So what happens on an exception is, okay, this is better probably. You essentially, if you have an exception, you flush the pipeline. So for example, this instruction that's the oldest in the machine had an exception. You flush the pipeline. What does that mean? You get rid of all of the instructions after this instruction. You get rid of everything in the machine, and then you basically copy the architectural register file to the physical register, to this front-end register file. Because you have the correct state over here, and its precise state at this point, and everything else it gets flushed in the pipeline, meaning that everything else becomes magically zero, invalid, and this architecture register file gets copied over here so that the system is in a precise state. Okay, so let me go over here. And that's what this sentence is about. And as a result, we have a system that looks like this. This is the out-of-order machine. This is the reservation stations that's used for scheduling or dispatching instructions in an out-of-order manner. And this is the reorder buffer. And the reorder buffer updates the architectural state in program order. Make sense? Okay, and that's your animal. Okay, so most modern processors, now I'm going to tell you exactly how modern processors do it. They use the following structures. They use reorder buffer to support in-order retirement of instructions, just like we've discussed. But they use a single register file to store all of the registers, actually. So it's not, I mean, there are some processors that use what I just discussed, but a lot of the modern processors, they use a single physical register file. There's a trade-off associated with which we're not going to go into. So this register file contains both speculative registers, meaning renamed registers, and also architectural registers, architectural state. And integer and floating point are separate. And to be able to distinguish between the front end and the architectural state, they have two different register maps. These are essentially pointers. So basically, there's a future front-end register map that's used for renaming, and there's an architectural register map that's used for maintaining precise state. And let me, before we do that, let me show you an example. So essentially, what we have is something like this. We have a pool of physical registers, physical register file, I'm going to call it. I don't know, let's make it 0 to 255, 256 of these. And this way, we're going to eliminate all of the data values that are scattered in the system. And remember, we had a front-end register file to use for renaming. Let's say R0 through R11, that's what we had earlier. It was actually R1 through R11. Now we're not going to have the values over here. Remember, we had the valid bit, tag, and the value. We don't want these values. We got rid of them. And whenever we rename R1, we're going to allocate a physical register for R1. There should be some mechanism to allocate. So R1, for example, this is not architectural. This is R1 at this point when we're renaming. R1 is renamed to, let's say, physical register 54. So tag will be physical register 54's ID. And any instruction that is going to be decoded at this point will get the tag physical register 54. And the instruction that's going to write to R1 will write to this physical register file. Make sense? So for example, let's finish this thought and then we're going to take a break. Let's assume that you have an multiply instruction that's writing to R1 and an add instruction that's reading from R1, right? We don't care where it's writing. This multiply instruction will first allocate a physical register for R1 when it's renaming. Let's assume that it's physical register 54. So R1 will be referred to as physical register 54 from now on. And when this instruction gets decoded, it's going to see that, oh, the tag is physical register 54, so it's going to wait for physical register 54 to be broadcast as a tag. And when this instruction wakes up, gets selected, just similar to what we've seen. There won't be any values in the reservation stations. The reservation stations will be just value tag. Valid bit, this valid, not to be confused with value, valid bit tag for both sources. And one of the tags will be physical register 54 over here. Initially, when this gets renamed, it'll be 0. When this broadcasts a tag, this instruction will compare physical register 54, so it will wake up, but there's no value broadcast. The value actually, when this broadcasts the value, it broadcasts into the physical register file and it writes the value to the physical register file. So there's a value that's associated here. And when this instruction wakes up, it's going to use the ID physical register 54 for its source and get the value from the register file. Make sense? This way, we actually eliminated the values, the storage of the values in the front-end register file, all of the reservation stations, by consolidating everything into this physical register file. We're connecting the writer to the reader, and the value is stored in just one location, physical register 54 in the physical register file. Hopefully that makes sense. You can think of it. Okay, so this is our front-end register map. Front-end register alias table. But we also have a back-end register alias table. This is not architectural, this is renaming. Whenever you decode an instruction, you update this with renaming. But you need to also keep the architectural state. Now, what does that mean? We need to have an architectural register map. Again, we don't want to store values. We want to store, well, architectural registers are always valid, actually. You don't need a valid bit over there, because it's your architectural state. It better be valid if you're running a program. So what you really have is just pointers. Now, what does this mean? This may sound confusing, right? Well, this means that some of your physical registers are actually part of your architectural state. And this makes sense, right? Whenever this instruction produced physical register 54, it wrote into R1, right? This instruction finishes execution. It writes into physical register 54. That version of R1 is actually here now. Now, when this instruction becomes the oldest in the machine, this physical register 54 actually houses the correct architectural value of R1, because this instruction finished. It's the oldest in the machine, which means that R1 should point to physical 54 over here in the architectural register file, right? So you see what I did? When an instruction becomes the oldest in the machine and it's completed execution, it basically changes the name of the architectural register to the physical register it is written to, because that's the oldest in the machine. It's produced the architectural value at that point in time, assuming it doesn't have exceptions, of course. Right? So that's exactly how a current machine works. You have this front-end register file register map for renaming. You have this architectural register map to keep the pointers to the architectural state, and this keeps pointers to the renamed state. And this way, you don't need to store values and broadcast values all over the machine. Values are stored just here. You just need to send the values whenever you produce them into the register file, and whenever you need to read a value, you read it from this physical register file. So if you go back over here, that's what exactly this slide means. You have a future front-end register map used for renaming and architectural register map used for maintaining precise state. So I showed you this picture earlier. Ignore the left part of it. The right part of it is something like Intel Pentium 4. This was actually Pentium 3. I said it incorrectly yesterday. This was Pentium 3. So if you look at Pentium 4, it's exactly a machine like what I've shown in this now messy picture. You have this front end. These are the architectural registers. These are all of the registers you have. This is the front end register alias table that points to the renamed values. And this is the architectural register alias table. They call it the retirement register alias table that points to the architectural registers. And sometimes they both point to the same register. Now, what does that mean? If the front end, assuming one register points to the same location over here, there's no instruction in the machine that is writing to that register. That's what it means, because the front end register alias table says that this register is mapped to physical register 55. The architectural register alias table also says that this register is mapped to physical register 55. This means that there should be no instruction in the machine that produces that particular architectural register. There's no instruction in the machine that's writing to it. Okay? And you also need the reorder buffer, of course. Okay, so this is a good place to take a break, and then we're going to continue. Okay, let's continue our exploration of out-of-order engines. But I should probably refill my water first. Okay. Okay, so hopefully now you have a good idea of what a real processor is. This is actually pretty much how all out-of-order execution processors operate today. There are, of course, a lot of other optimization that goes on in the system, which we don't have time to get into. And if you ever get the chance to work on an out-of-order processor, take that chance, because it's the amount of things that you learn from that process is really amazing. I cannot even go through all of them right now, but these are the architectural high-level principles at this point. So what we've done essentially is, by doing what I said, is we've consolidated all of the values into this physical register file, such that the values are not all around the processor. They're all consolidated here, and you can, whenever you need to access a value, you basically use the physical register ID that you're waiting for, index the physical register file, and get that value. Whenever you need to update a value, you send the value to the destination physical register that you're writing to, and that gets updated in the register file. So that's beautiful. Nothing stores values other than the register file at this point, at least register values. And also, this could be very, very big, actually. Of course, limited by the timing issues and the logic that you have. But you can have a 1,000-entry register file over here. It could be very large. You're not bound by anything. Basically, if you need to rename a register many, many times, you need to create new physical registers that it gets renamed to, and having larger number of registers helps that, so that you don't need to stall the processor. Okay, so let's cover the concepts a little bit. This is, by the way, we're going to get a little bit more complex later on when we talk about loads and stores. We haven't even touched loads and stores. That's the most messy part of the system. But when we get to that, you'll see that it's going to be even more complex. But let's recap some of the key concepts. Basically, how do we enable out-of-order execution? We need to link the consumer of a value to the producer, and we do this through register renaming. We associate a tag with each data value, and the tag is now the physical register ID. And then we buffer the instruction until they're ready. By inserting them into the reservation stations, we keep track of the readiness of the source values of an instruction in the reservation station. We broadcast a tag when the value is produced. Instructions compare their source tags to the broadcast tag, and if matched, the source value becomes ready. And at that point, they can take the physical register ID that they're waiting for and go access the register file and get the value from there for both of their source registers. And when all source values of an instruction are ready, you dispatch the instruction. Actually, I went ahead of myself. You need to wake up the instruction and select the instruction, and then it accesses the register file after that. Right. Okay, so that's basically it for out-of-order execution. So let's think about what these enable. So register renaming eliminates false dependencies, as we said many times. It also enables linking of consumers with the producers. And buffering in reservation stations enables the pipeline to move for independent instructions. Before, the problem was that we had an independent instruction that's coming later, but we have nowhere to put this dependent instruction. Now, buffering in reservation stations enabled that. But we cannot just do buffering. We need to do all of this to actually enable out-of-order execution. And tag broadcast enables communication of the readiness of the produced value between instructions. And wake up and a select enables out-of-order dispatch. So once you have all of these components, what you have is an algorithm for out-of-order execution, which is called Thomas-Low's algorithm. And this is, as you've seen, you can basically, we've built the data flow graph in the machine. It essentially dynamically builds a data flow graph of a piece of the program. That's why it's also called restricted data flow. It's restricted to some part of the data flow graph. Which piece? Basically the piece that's in the machine. That's in all of these reservation stations. Or we'll call that as the instruction window. Basically, the data flow graph is limited to what's called the instruction window. Some people call it the active window. It's all of the instructions that are decoded, but not yet finished, not yet retired, not yet committed. So somebody may ask the question, can we do it for the whole program? well, then you need a lot of reservation stations, for example, to keep the data flow graph for the entire program, right? Why would you like to? Because you want to execute a lot of things in parallel, right? So you actually, if you actually have a lot of latency between instructions, you may, for example, if a load instruction takes 1,000 cycles, then if you want to keep fetching and keep executing instructions, you should have at least 1,000 entries in your reorder buffer, right? Because the load at some point is going to be the oldest instruction, it's going to wait for 1,000 cycles. If you don't have enough entries in your instruction window, then you will not be able to decode instructions. You will need to stall the machine. That's why you would like to make it bigger. But of course, making it bigger is not easy. So making it bigger means that you need to have a large instruction window. And it's not easy to do with the algorithms that we've discussed, because basically you need to have a huge physical register file. You need to have all of these tag broadcast buses, which is very difficult to eliminate. Although people actually optimize that in real machines as well, but we're not going to go into how they optimize it. But it's not very efficient. So scaling the size of this circuitry to a very large instruction window sizes, thousands, 10,000, is not easy. So today we're around 250 or so. In the past we were much smaller. Okay, so I think we already said this basically. We get a data flow graph. That's why it's data flow. Okay, so before we go into a little bit more complexity, let's talk about why this is beneficial. Let me ask you the question. What if all operations take a single cycle? Is this useful? This may require some thinking. If all of my operations were a single cycle, add, multiply, doesn't matter, everything was single cycle, would I get benefit from an out-of-order machine? Some people are saying no. No? Okay, and that's the right answer, actually. No, because there's no point. The instruction is going to produce the value in the next cycle, so you can actually bypass it to the next instruction. Basically, this is out-of-order execution is a way of dealing with long latencies. Another way of thinking about it is you basically tolerate the latency of multiple cycle operations by executing independent operations concurrently. If all of your instructions were a single cycle, there is no reason to do all of this. But real world is not that simple, so everything takes a heterogeneous amount of time. So a load may take 1,000 cycles, maybe more. An add may take 1 cycle. So that's how you can. That's why out-of-order machines are beneficial. So what if an instruction takes 1,000 cycles? I already said this actually. How large of an instruction window do we need to continue decoding? Basically, you need 1,000 entries in this case, assuming that it takes 1,000 cycles after it becomes the oldest instruction in the machine, right? Yeah, basically, you can tolerate as many cycles as you have buffering for. I have a lot of questions over here, which I'm not going to fully answer. But what limits the latency tolerance scalability of Thomas Low's algorithm? Basically, how big you can make this instruction window size. If one of the instructions take 5,000 cycles, you need to make it 5,000 instructions large so that you don't need to stall decoding. Now again, as an architect, maybe you don't want to do that, right? You want to analyze how often do you see these instructions that take 5,000 cycles. If you don't see them that often, maybe it's okay. But if you see it 25% of the time, maybe you should increase the instruction window size so that you don't stall as much, right? Yes?
Why don't we use the DataFlow architecture?
We'll get to that. Yeah, I've already given you the answer, but we'll get to that. Basically, the reason is you don't have precise exceptions in DataFlow. You cannot program it easily. You cannot make sense out of it. Whereas this internal thing is great because you can program it, you can debug it nicely, you have precise exceptions because you're still following the von Neumann model. That's the main reason. But we'll get to that again soon. So basically, what limits the latency tolerance is the instruction window size. How many decoded instructions, but not yet retired instructions, you can keep in the machine. And again, hopefully, it's intuitively clear to you that increasing the size of this is not easy. Yes?
Is the window size the combination of the ROB size and the size of
reservation stations? Yes, absolutely. It's really a combination. But people try to minimize the size as much as possible because it consumes power. So ROB size may be larger than individual reservation station sizes. Because if ROB, reorder buffer doesn't need to, reorder buffer, so reservation stations don't need to hold the instructions that have finished execution but not yet retired, whereas ROB needs to hold those. Okay, so that's, hopefully you're doing the readings. How many of you have done this reading? Okay, more people compared to yesterday, which is good. It's an improvement. So this is from your reading, and this is essentially what we kind of discussed, although there are other things over here that you don't necessarily need to know at this point. You basically, this is the decode, rename, dispatch logic, and you send them to these buffers that are essentially the scheduling window. These are the reservation stations, and then they access the functional units, and this is the reorder and commit. And you can see that there's a single register file over here. It's not, I mean, there's floating point and integer, but there's a single physical register file. So if you look at a modern design, again, I don't expect you to understand everything over here, but it has pretty much a lot of the concepts that we have over here. So if you look at this allocator register renamer, it gets instructions from what is called the trace cache, which is a special form of instruction cache. And it renames the registers, and then it sends the instructions to different reservation stations, as you can see. Memory scheduler, this is the memory part. And it has a floating point unit scheduler, simple floating point, or slow and general floating point unit, and a fast integer ALUs, as you can see. And you can see that this scheduler feeds two ALUs over here, and there's a slow scheduler. Scheduler is really the reservation stations that feed this complex one. But before you get into the reservation stations, you need to get the values from the register file or the bypass network, as you can see. So it's very similar to the machine that we built at the end. You have a single physical register file that you need to access before you actually execute the instruction. Is there anything else that I need to show over here? I guess not, but this is just to give you an example. We're going to touch this unit, which is the most messy unit in this soon. Okay, this is my simplified picture from my own PhD thesis, actually. I like my own picture better. But you can, maybe I'm a bit biased. But you can see that there's a renamer over here. That's the front-end register alias table, and then you send instructions to different reservation stations, FP, int, and memory scheduler, and then you have the physical register file for floating point, physical register file for int, integer, and then you schedule instructions to the execution units. And then there's a reorder buffer over here at the end, eventually, and then there's a retirement register alias table. You can ignore this part. This is what I proposed in my thesis. Another machine, Alpha 21264. This is one of the fastest machines of its time. Actually, this is the fastest machine of late 1990s. And you can see a very similar structure. We'll cover bench predictors later on, but into register renaming. And here you can see the cycle by cycle what happens. This is how they divided the stages. So they had a renaming stage over here, and then they had, this is essentially, they called it the issue queue, but this is the reservation stations for them. And when an instruction becomes available, it accesses the integer register file, and then it goes to the integer execution units. Now, they were so tight on timing that, in this case, they duplicated the register file. They have two copies of the integer register file, because they wanted to be able to send two instructions here and two instructions here. So we didn't talk about the concept of superscalar execution. We're going to see that. So far, we've executed, well, maybe one instruction, but you can actually do two instructions here and two instructions here. And in order to be able to do that, assuming that two instructions, assuming that you want to execute 4 instructions in a cycle, each of them is reading 2 registers, you need to have 8 ports to the register file. They said this is too complex for us to design within the cycle time constraints, so we're going to design a 4-ported register file and duplicate it, and ensure that they remain consistent. So that's why you have these 2 integer register files over here, so they can execute 4 integer operations. So, and that's the pipeline that they had. It's a relatively shallow pipeline. So it's another machine, MIPS. Did Frank tell you what the MIPS acronym stands for? MIPS? Anybody? It's not millions of instructions per second. That's a different acronym. MIPS initially was a design that came out of the philosophy that hardware should be extremely simple. This is the philosophy of reduced instruction set computers or simple computers. They basically said, we're going to make hardware extremely simple. All of the code scheduling will be handled by the compiler. So we're not going to have any hardware support for dependency checking or interlocking. So MIPS means microprocessor without interlocking pipeline stages. So that was their vision in 1980s, early 1980s. They wanted to have very simple hardware. And the compiler schedules the instructions. It handles the scheduling of the instructions so that you don't have dependency issues in the pipeline. And initial MIPS designs were like that. They quickly figured it out that it's very low performance. So this is one of the latest MIPS designs. You can see that it's very heavily out-of-order execution. So forget about interlocking. They added a lot of hardware to make it high performance, because it was not easy to have simple hardware and get high performance out of it, because you just cannot deal with these long latencies easily in the compiler and variable latencies easily in the compiler. That's why the vision that said there should be very little hardware, there should not be even support for interlocking. In fact, the initial MIPS said we don't even want floating point units. If you want floating point, do integer operations to get your floating point. Oh, no, it doesn't work. If you want performance, you really need this complexity over here in hardware. So as you can see, this is very similar to what we've discussed. You have a register map table front end, and you have the schedulers over here, and you have the register file over here, and then you have the functional units over here. And they don't show the other stuff over here, but that's fine. But there's another interesting thing that show here. Basically, they have these free register lists. Basically, this shows that you need to allocate free registers, because there's a physical register file. You need to decide when a physical register becomes free and when it's not available. And I'll let you think about that. I think one of your colleagues thought about that already. This is IBM Power 4. It's also relatively old, but it's very similar again. And again, I'm not going to go through this in detail. So IBM Power 4, it was one of the first multi-core machines, actually. But each core had out-of-order execution and had a 100 entry instruction window. And it was an 8-byte superscalar machine. It was able to fetch and decode and execute 8 instructions per cycle. We're going to get to superscalar execution later. And it had a hybrid branch predictor, which we're going to cover later on. Okay, this is IBM Power 5. What they did was, it's essentially the same machine, but they added multi-threading on top of it. We were able to execute 2 threads. And this is a general purpose processor. These power systems are used heavily in the financial world. And actually, it's not just one processor. It's really a collection of many processors. So if you want to buy one of these, you need to pay IBM $1 to $5 million or so, probably. So you cannot just buy it as a single machine. So if you have deep pockets, you can have one of these. But it's very similar again. I mean, you see that there's, well, it's not very nicely shown over here, but these are the issue queues. Again, it's the schedulers, and then they select, and then they access the register file over here. And after they get the source operands from the register file, they execute over here. These are the execution units. And then this is kind of like a pipeline diagram. And then you write the register file at the end. And then group completion is their name for the reorder buffer, basically. Have you completed the instruction at this point? Okay. Okay, now I can go on and show ARM Cortex-15 or whatever, but we're not going to do that. Basically, all of the machines that are out there today, in this, for example, I have an out-of-order machine that's running efficiently and at high performance. Okay, now you know the basic principles of it. Now let's talk about the most hairy part of an out-of-order engine, which is handling of loads and stores. Now this is going to be, I don't want to spend a lot of time on it, but it's really important to understand that memory is the really most hairy part. So we've talked about registers. Actually, handling registers added a lot of complexity to the system, right? But it's actually the easy part. So we considered mainly registers as part of the state. What about memory? There are multiple fundamental differences between memory and registers. The first one is really interesting because it's going to cause a lot of complexity and headache in the design. Register dependencies are known statically. Meaning, you look at an instruction, it sources register 3, you know the sources, you know the destination. Good, you can do renaming easily, right? Because you know everything at the front end of the machine after you decode the instruction. But memory, you need to execute the instruction a little bit to get the address. So you don't know the memory address of an instruction at the beginning of the pipeline in the decode stage. And this is the cause of all of the headaches that we're going to have. On top of this, these addresses are not small, they're large. So register state is very small. We looked at 32 registers, 64 registers. Memory state is huge. The addresses are very large, right? So this is going to double our headache a little bit. And the register state, this is also interesting, but we're not going to tackle it as much. If you look at other threads or processors, they don't share the registers normally. Whenever you write a multi-threaded program, for example, different threads don't share registers. So you don't need to worry about them. But memory state in a shared memory multiprocessor, which is most of what multiprocessors are today, is shared between different threads and processors. And this could cause headaches if you update memory state in an out-of-order manner. But we don't want to update memory state out of order anyway. But we're not going to tackle this one. But this is another difference between registers and memory. So the first two problems are going to cause us headaches with out-of-order execution. The last one we can perhaps handle. There are some issues over there, but you really need to take the advanced architecture class to understand them. And those are also hairy issues, by the way. Okay, so what are the issues that are caused? Basically, if you have an out-of-order machine, you're executing instructions out of order. You need to obey these memory dependencies also. It's not just about registers. You need to ensure that memory dependencies are correctly obeyed, meaning that a load may be dependent on a store, and you need to ensure that load gets the correct value from the correct store. Now, we handle this nicely with register renaming, but these are not registers. These are memory addresses, right? Register addresses we know at the beginning of the pipeline, so we can rename nicely to other namespace. Memory addresses we don't know until we execute the instruction. Okay, and we need to do so while providing high performance. So that's the problem, basically. The key observation and key problem is that the memory address is not known until a load or a store instruction executes. So first corollary is renaming memory addresses is difficult because of this. You cannot do it at decode stage. If you really want to do renaming, you need to do it over here. But that's too late, because things are already out of order over there. The beauty of renaming was when you're doing the renaming, it's in order, so you can link the producer to the consumer correctly. Here, it's a mess. Okay, because one instruction may have generated an address in some way, another instruction may have generated an address another way. So let me switch to this very quickly. I think we're going to switch back and forth a bit. So let's assume that we have a program, you have a store instruction here. It basically computes an address based on R5 and with some offset. And then it writes, I don't know, R10 over here. And then we have a load instruction that computes its address based on R25. And then writes the result into whatever register. It's not important. This is also not important. So the key question is, when this executes, it generates an address, A. When this executes, it generates an address, B. Is this address A dependent on B? Well, if you knew addresses A and B, that's great. You could compare them. But what if this executes earlier? Because you're doing out-of-order execution, this store may be dependent on something that takes 1,000 cycles, but this load may be dependent on something that takes 2 cycles. So this load is ready to go. It generates its address. It generated A. The store is up there still waiting for R5, for example, or even the source register. Maybe both of its source registers it's waiting for. So you have no idea what the address of the store is, and you want to execute this load. There's a problem, right? Because if the addresses are going to be the same, you want to get the value from the store. So what do you do? And that's the key problem. So we're going to take a look at that a little bit. Okay. So essentially, determining the second corollary, what I showed you is determining the dependence or independence of loads and stores has to be handled after their partial execution. I say partial execution because load kind of has it generates its address, and then it loads the value in that address to a register. But address generation is just partial execution of it, the load. The next step is going to the memory and getting that location. But if you don't know if a store is writing to that address, then maybe you should wait. Okay? And there's also another corollary 3, which is also what I discussed actually. When a load, let's assume we're talking about loads right now. When a load has its address ready, there may be older stores with unknown addresses in the machine. And the other way around also works. When a store has its address ready, there may be younger loads with some unknown addresses in the machine. The first one is more serious, of course. So let's take a look at this. Basically, this is essentially the example that I showed you. When this load has its address ready, it doesn't know if the store is writing. What may be worse is there may be another store whose address is also not ready. And this load may be reading, let's say, I don't know, 4 bytes over here. And 1 byte may come from here, and 1 byte may come from here. So it's actually much more messy than you may actually initially think. There may be actually many stores writing to these locations. So you need to actually get the value correctly to be able to do that. Okay. To basically get the correct result, right? Okay. So we're not going to solve the entire problem. I'm going to give you the complexity of the problem and some approaches to handle it. But believe me that this is the messiest part of an out-of-order execution engine, and this is the least scalable part of an out-of-order execution engine. If you thought that it was really the tag broadcast logic, you're wrong. It's really this logic that disables the scalability. Okay, so the key question is, when do you schedule a load instruction in an out-of-order execution engine? As I said, the problem is a younger load can have its address ready before an older store's address is known. This is also known as the memory disambiguation problem. You disambiguate addresses, or the unknown address problem. I like the unknown address problem because it's simple thinking, unknown address. So there are multiple approaches to this. One is the conservative approach, which is terrible for performance in general. You stall the load until all previous stores have computed their addresses. You can do that, right? In this example that I've shown you, I'm not going to switch to it, but there are a bunch of stores in front of older than this load. You basically wait until all of them compute their addresses. It doesn't matter if it takes 1,000 cycles, 5,000 cycles, you just wait. And when all of them have computed their addresses, now you know which store you're dependent on. You need to do something to know that, of course, but you know. Or, I mean, if you're even more conservative, you just wait until all of the stores are out of the machine, meaning all of them have retired and updated the memory. But that even takes longer, as you can imagine. So this is the conservative approach, and this is terrible for performance. Aggressive approach takes exactly the opposite. It basically says, I'm a load, I know my address, I'm going to assume that I'm independent of any other previous stores. I'm going to schedule this load right away. Okay? That's aggressive. Basically, the prediction is that hopefully this load is not going to depend on any of the stores. Of course, if you do this, you need to check later on. Did I actually predict this correctly? This is a method of, this is an example of predicting something in a machine. So this actually also doesn't work extremely well, although it's usually better than the conservative approach. But it adds additional machinery to check, basically. If you're wrong, you should re-execute this load and get the correct value. So if you're wrong, you flush the pipeline, basically. Okay, there's also an intelligent approach, which pretty much all existing machines employ, which is essentially more intelligent, as I said. You predict with a more sophisticated predictor if the load is dependent on any unknown address store. Okay, so let's take a look at this a little bit more. As I said, a load's dependent status is not known until all previous store addresses are available. There are two questions, actually. One is, how do you detect the dependence of a load instruction on a previous store? You wait until all previous stores are committed. In this case, there's no need to check for address match. The logic is simple. Or the second option is you keep a list of pending stores in a store buffer, this is also called a store queue, and check whether a load address matches a previous store's address. So basically, okay, I'll get back to this later on. And the next question is, how do you treat the scheduling of a load instruction with respect to previous stores? You assume all load is dependent on all previous stores. You assume load is independent of previous stores, or you predict the dependence. Of course, if you want to predict the dependence, somehow you need additional logic for that. So let's take a look at this one. First, if you assume a load is dependent on all previous stores, this is good because you don't need to add any logic. You just wait until all previous stores are done. But it's too conservative because it delays independent loads unnecessarily, right? Again, in this example, these stores take 1,000 cycles, this load is ready, and if it's independent, you basically delay this load for 1,000 cycles. If you do option 2, assume the load is independent of every previous store, it could actually be simple, and it's a common case. There's no delay for independent loads, but we have to pay the tax for recovery. If you're wrong, first of all, you need to figure out that you're wrong. So there needs to be some additional logic that says, you sent this load, you executed it, but you were wrong. So there needs to be some checking that needs to happen. When the store computes its address, it needs to check, okay, whether if there was a load that actually assumed that it was independent of the store. So that's a mess. So basically, it requires recovery and re-execution of the load. So existing machines actually flush the pipeline whenever they're wrong. The option 3 is the intelligent option. You basically predict the dependence of a load on an outstanding store. I'm not telling you how to actually do that. There are mechanisms for this. Actually, this was the subject of a very prominent legal battle between one university, whom I will not name, and a bunch of companies that the university claimed that they actually patented this work, and the companies used some sort of memory disambiguation, and there was a huge legal battle that lasted for a really long time. You can probably figure that out. Okay, but this is more accurate, clearly. Because load store dependencies actually persist over time, people found out that if this store is writing to a location that this load is going to read, whenever you go back to the same load and store in a loop, for example, it's going to happen again and again and again. So you can learn from past executions. But of course, if you're wrong, you still need to recover and re-execute. And there are some very interesting papers. For example, the alpha 21 to 64, if you read this optional reading, you will see that whenever it executes a load, initially it assumes that the load is independent. It figures out if it's right or wrong. If it's wrong, the next time it says, I'm not going to assume that it's independent, I'm going to assume it's dependent. So it basically learns over time a little bit. Okay, so this is very quickly, this is showing the conservative approach, no speculation, aggressive approach, and the perfect approach. And this is performance on the y-axis, instructions per cycle. And these are some workloads that people have used in 1990s, as you can see. Some of them are interesting, like Go benchmark. It plays Go. GCC is a compiler. Compression. So these are actually still used, some of them. But basically, if you look at this, conservative approach is actually terrible. Aggressive approach is a little bit better, but perfect approach has a huge gap. So that's why you would like to handle this well. So simple predictors can achieve most of the potential performance. Okay, I'm not going to talk about how to do the prediction. You can leave that to your imagination. But let's talk about data forwarding between loads and stores also. So we cannot update memory out of program order, clearly. That we cannot even update registers, because that would violate sequential semantics. Which means that you need to buffer all store and load instruction and instruction window, and we know that. We could use the reorder buffer for that. Now I'm going to sidestep the problem. I'm going to say, even if we know all of the addresses of past stores, this is still complex. So when we generate the address of a load, two questions still remain. One is, how do we check whether or not it's dependent on a store? So there needs to be some way, assuming that you would like to schedule this load. At that point in time, you don't want to take the conservative approach. And how do we forward the data to the load if it's dependent on a store? So for this, you need a special structure. And these special structures are usually decoupled into load queue and store queue for this. It can be combined between load stores. For example, Pentium Pro in Intel it was called a memory ordering buffer, MOB. So you had a MOB in a processor. But you can combine and separate, basically, you have a load queue and a store queue. So whenever you want to, you produce the address of a load, what you do is you search the store queue to check if there's any store that you're dependent on, so that you can schedule the load. And a store, when it finishes execution, when it computes its address, it searches the load queue to see if there is a load that's dependent on it. This is the second one is needed if you're doing prediction, so that you can check your prediction, right? If you predicted this load is independent, and you've executed it, but then the store address became available, and then the store needs to check if any of the loads got the wrong value because they were predicted to be independent of the store. So I'm not going to talk about the second case, but it's also needed if you're doing intelligent prediction. But the first case is needed even if you're not doing prediction, you just want to be able to decide whether this load is dependent on a store, and even assuming that you know the addresses of all of the previous stores. Okay. So when a store instruction finishes execution, it writes us the address and data in its reorder buffer entry or the store queue entry. When a later load instruction generates its address, it basically searches the store queue with its address. So we're going to look at how bad that search is. And it accesses memory with its address. And it receives a value from the youngest older instruction that wrote to that address, hopefully. So to be able to do this, you need a complicated search logic. And this is actually, remember the content addressable memory that I introduced in the previous lecture? This is the worst content addressable memory that you have to enable out-of-order execution of loads and stores. So content is really memory address, but you also need other stuff, like the size, like the age also. So let's take a look at this. This is called the store-to-load forwarding logic. So basically, I'm going to make it simple. This is a store queue. This is an in-order list of all of the stores that are in the machine. You have a head. This is all hardware, of course. You have a tail. And what do you have over here? Clearly, you need to have a valid bit, whether this is valid, and then address of the store, which could be 64 bits, and then a data value of the store if it's available, which could be 64 bits. And the valid is 1 bit. And of course, you need to also have valid bits to see whether the address of the store is valid and whether the data of the store is valid also, which makes it really interesting and complicated. Because the store executes, if the store hasn't computed its address yet, its address is not valid. But the data may be available, right? You're in an out-of-order engine. The data may already be ready. Okay, so whenever a load instruction, so let's assume that you have a store here at address A. Let's assume that addresses are all known. I'm going to make it even simpler. Now let's assume that you have another store here. Okay, A, B, C, D. All stores are here, X. And we have a load over here that computes its address. And let's assume that, I don't want to call it, let's assume that it computes an address Z. The key question is, where should this load get its value from? So what it needs to do is it needs to compare this Z to all of the addresses over here. So basically, for each entry, you need to have a comparator, right? That sounds terrible already. It's going to become more terrible. And this is a 64-bit comparator, assuming your address is 64 bits. I mean, I exaggerate a bit because normal machines don't use the entire 64-bit address space. Let's assume that it's 48 bits, okay. That's more realistic. So it's a 48-bit comparator of address. And you do this. But is that enough? That's not enough, right? I've given you an example earlier where one store is writing to 1 byte over here, another store is writing to another byte, and this load is reading these 2 bytes. So you may actually match in multiple places. That's the first observation. It's not a single match. You really need to match in the multiple, the latest locations that you're trying to read. So it's really, there could be multiple locations, and also you'll need to get the latest stores that write to that location. And also, what makes it a little bit more complicated is you need to ensure that the size also matches. So let me actually go back over here. I'm not going to build the complete logic over here, clearly. If you get a chance to build it for sure. But basically, this is the complexity of the search. It's a content addressable search based on the load address, as I showed you. It's a range search, meaning based on the address and size of both the load and the earlier stores, because you may partially overlap with the address, right? This load may be accessing bytes 8 through 12. The store may be writing bytes 11 through 12, right? It's an age-based search. You want to get the last written values. And that's essentially what you need to build over here. Now, on top of this, load data can, let me go back actually over here to the DocuCam. So you need to find the latest stores. Assuming that, let's say you're loading addresses Z, Z plus 1, Z plus 2, and Z plus 3. Oh, you cannot see it? Okay, sorry. So basically, you want to access addresses z, z+1 because it's a 4-byte load. You need to be able to ensure that you find all of the stores that are writing to all of the latest writers to each of these locations. Now, you may be able to find one that's writing here, another that's writing here, another that's writing here. Okay, 3 stores are writing here. Where do you get the 4th one from? Well, now you need to access memory for that, because there's no load store that's writing to that one. So it's actually, to be able to get your data value, you need to search this, and you also need to access memory. That's why this is one of the most complicated parts. And when you search this, of course, there may be no match. Then you access memory, of course, to get all of it, right? Because there may not be any stores that are writing to the location that you're reading. At that point, you need to access memory. So this search may be useless, but you need to do it to ensure that you get the correct value for the load. Make sense? Yes?
So the store queue isn't just used to check that there aren't any erasers, basically, so it's also, it can also be used as a pipe test to get the value.
Exactly, exactly, exactly. You could use it to check, of course, but if you have a match, you need to get the value from somewhere. Yeah. So it serves 2 functions, basically. It serves the function of, can you schedule this load? And if the load is actually dependent on a store, give the value for data forwarding. Okay, I already said this, basically. This is the last example that I gave. Any questions? Is this clear? The complexity? I'm not going to ask you questions on the load store forwarding logic. But you should really know that this is really the tough part. People try to scale the size of the instruction window. Yeah, they can scale the reservation stations, but it's very tough to scale this logic much larger. I believe existing processors maybe have a 24-entry store buffer, even though the instruction window size may be 256 or so. So it's very small compared to other parts of the machine, and you're usually limited by how many stores you can put into the machine because of that reason. So if you keep putting a lot of stores into your machine, you're probably destroying the performance of your machine. So try not to store much in your machines. And the reason is because of this, basically. This is very hard to scale, and the machine cannot have a lot of stores in it. Okay, if there are no questions, this is a good place to stop. Next time, we'll start with other approaches to instruction level parallelism. And have a good weekend.